Hello everyone, and welcome to today's webinar where we'll be taking a look at the energy performance gap in buildings and what can be done to improve this. My name is Stephen Kennett and I look after the built environment and energy channels here at 2 Degrees. I'm delighted to welcome our two presenters today. We're joined by Sunil Shah of Aclara Advisory, who has a wealth of experience in this area, and also Anna Menez, Group Energy Manager at Tesco's. Today's presentations will last for around 35 to 40 minutes, which will leave us with 10 to 15 minutes for questions at the end. Before we begin, I'd just like to remind everyone that you can submit questions throughout the webinar using the Q&A box on the bottom right-hand side of the screen. Just type in your question and press send, and we'll wait until the end before answering as many as we can. As an aside, if you should have any technical issues during the presentations, please use the chat box on the right-hand side to send me a message, and I'll get back to you as soon as I can. So without any further delay, I'll hand over to Sunil, who will get us started with today's presentation. So over to you, Sunil.
Brilliant. Thanks very much, Stephen. Good morning, everybody. As Stephen mentioned, my name's Sunil Shah. I'm a director with CBX, and what I'll go through in this presentation is a quick overview in terms of the energy performance gap that we have, and then talk through in terms of the CBX program that's taken place, which is a not-for-profit activity that we're working with UCL Energy Institute on, in how we're looking at providing an evidence-based approach to be able to close that gap, provide information to end users to better inform them on the activities which they can provide at design, construct, commission and operational stage. Okay, so first of all, in terms of the problem itself, and this is something which Anna will go into in more detail in the second presentation, but as an overview, we have a significant problem in terms of the gap between the design and the design predictions that we are expecting, and then the actual operational performance of the building. And throughout all of that, we have performance values of up to 2.5 times difference. And so what we mean by that is our expectation of energy consumption at a design stage may be £1 million of energy spend for a building, and an operational stage 2 to 3 years in, it may be 2.5 million, which is a significant difference and a significant change as part of that. And in terms of the reasons for that, we've got a variety of issues that arise. And what we look at is 3 areas that aren't necessarily joined up at a policy level and at a delivery level. So we look at buildings, we look at energy, and we look at carbon. But all these 3 are looked as individual silo activities rather than necessarily looking at them as a cohesive, joined-up process. So first of all, we have a series of building-related policies that aren't linked together and aren't structured. Most of the policies, processes that we have in place come from the European Union, and the European Union focuses very much on energy. So all of the directives that come out, the Energy Performance of Buildings Directive and the various other, the Energy Efficiency Directive, is very much focused on energy. So the UK is unique in that approach, that we look at carbon as a primary mechanism as opposed to energy. And so we have our first challenge, which is how do we translate a lot of the information which comes out from the European Union, which is written as energy requirements and as kilowatt hours, and how do we translate that into a carbon reduction when we have different carbon loads for gas, for electricity, and from various other energy sources that are coming through. And so because of that, the policies that we have in place are very fragmented and not well structured together. And a lot of them are design-based, so we have energy performance certificates, which is very much a design rating. We have display energy certificates for the public sector, but that doesn't necessarily reflect the performance of the building itself. Those are normalized values which are being used predominantly within them. And we don't have much of a driver in terms of the reporting of operational use of energy, or certainly in terms of encouraging its reduction. So we have the forthcoming ESOS program, the energy audits program, which is due in place fairly shortly, together with display energy certificates requirements and together with energy performance certificate requirements. All three of these require reporting to take place, but none of them require any action to take place as part of that reporting. And so where we are is, with a lot of the upfront loads and the changes in regulations, we focus very much on regulated loads, which is the loads from a design perspective that we understand and that we're more in control of, and what's classified as unregulated loads, which are the loads which are very much user-based. So this is small power units, but it also includes things like catering, as well as the computer facilities and computer suites which can go into buildings, are all outside of the scope. And yet increasing evidence coming through is showing that that adds a significant margin and a significant additional load to the energy. So at the end of the day, we aren't guessing the savings in the real world. We're making those predictions, we're making an assumption on the amount of savings, but we're not seeing that translated at the end level. And part of that is because we have a huge amount of reporting requirements that I've mentioned, whether it's Part L reporting, energy performance certificates reporting, feed-in tariffs, renewable heat incentives, the GLA in terms of the planning requirements which are in place. But they all look at completely separate things. And so we're not measuring apples for apples, we're almost making a fruit salad out of this. So there's a huge variation that's taken place. And so there's a question that I'd like to ask everyone. And Stephen, is this as a poll for everyone to answer?
Yep, so I'll start running the poll now, and everyone can add their answers. Okay.
So the question here is, I've mentioned the number of regulatory requirements which are in place, and that the government's putting forward around energy efficiency, in particular for buildings. So energy performance certificates, display energy certificates, the energy auditing program through ESOS. And so the question is, whilst reports are made, should the implementation of the recommendations be mandated? And there's three answers. The first one is yes, the second one is no, and the third one is a qualified yes. And that's a variety of qualifications, but it's based upon whether we should take a certain payback criteria in place with certain costs in place, and therefore there's a threshold of recommendations that are put forward, and below the threshold they aren't put forward.
Okay, so I've got the results coming back now. So 86% of people are saying yes, so quite an overwhelming response there.
Fantastic. Yeah, we'll just try and feed that through to DEC as well now. And in part of how do we get to this position in terms of where we start off with the performance gap and where we end up? And this comes from a piece of work which Bill Bordas has been heavily involved in. These slides come from Bill, and I was also involved in this project. And what we have here is a design of a headquarters building for an organisation, which was intended to be very low carbon. And so at its initial starting point, the initial design was at 15 kilograms CO2 per metre squared. And what we've got below that, the three bottom bar graphs show the benchmark figures against Econ 19, which is the last set of data that we have available as in terms of nationally available benchmark figures for energy use within buildings. And there's a key in there, and what the key shows is all the different types of energy usage that takes place within the building. And then from the design information that we have that was put forward, the efficiencies and the total load of the building went up slightly, up towards 26 kilograms, and then of that was 5 kilograms of CO2 that was discounted because it was provided through PV and solar cells that were placed on the roof. So we had a net consumption of 21 kilograms. We then looked at what the logbook rating was, and the logbook came out as being significantly higher. So this came out at towards 48 kilograms, so almost double the original design claim that was being made. And then we looked at the actual use in 2006. This is when the building was operational in its first year. And we see a figure there of somewhere in the region of just over 80 kilograms of CO2. And that figure is actually in line with good practice for an air-conditioned office. So what was originally conceived as being best in class and significantly lower turned out as being a good practice benchmark. But that isn't the whole story. What we're seeing is there's major differences in the regulated loads that we have. So in the purple bar, you start to see the regulated elements as being significantly above. But the major factor that we have is that over 50% of the CO2 comes from the server room and from the kitchen. Now, these are unregulated emissions that hadn't been factored in originally, hadn't been understood originally, and therefore would have significantly increased the original design claims that were being put forward. And the challenge here is if we don't understand these energy loads at the initial design stage, are we able to factor in how that energy gets provided and how the building operates with those additional loads? And so we have a stage program, and in terms of the energy performance gap, the reasons for that gap, there's a multiple set of reasons, but they're not unknown. So at the design stage, some of the issues come from inaccurate predictions of how we're intending to use the building, but also unachievable quality of construction. And we've seen commentary of air tightness figures that are significantly higher than is realistic to be able to be achieved. Within construction, we have poor attention to detail, with missing insulation that takes place. Again, so we end up with a fabric of the building which is much poorer than we intended to provide. From a commissioning perspective, we have in general poor commissioning throughout, and that's not only of the HVAC systems, the heating, ventilation and cooling systems, but it's also commissioning of the meters which are being installed into the building, which then potentially can provide poor data of the performance of the buildings. And then from an operational perspective, we have not only the overcrowding that takes place and the addition of people that goes within a building, but also a misunderstanding of just the human behavior within buildings themselves and how humans react to different conditions and different circumstances that take place. And that's very much from a cultural perspective, and clients will be different at each level, but we do have some common approaches that do reoccur throughout them all. And so what we're looking at is a robust and structured approach to how we count energy, from a starting point, which is defining a need, right the way through the brief, the design, the construct and the operates process. And it's how we feed knowledge through this entire methodology from the initial stage through to the end point. So we end up with a circular process, and the image at the bottom left-hand corner is a previous project that we've been involved in, and we had an overlay that was placed upon the organisation's capital management programme, and it started off with an initial meeting and went through a structured approach. But all of that structured approach was based upon an understanding of the energy performance and the overall sustainability performance that the organisation has from the existing portfolio and from wider benchmarks, being able to use that data and the information to inform the original project brief. So we had a project brief which had fixed numbers in there in terms of an expectation of energy performance. This is kilowatt hours per metre squared, energy performance within a building, as well as other factors that we included in there from a transport perspective, a water consumption perspective, and so on. And that led to a very different process, whether it was a refurbishment project taking place, a new build project taking place, or even a leasing of a floor or two within a building. And the process there was using the existing data and information to inform how the new portfolio would then operate. And this is really where CBX comes in. What we're trying to provide with CBX is an open and transparent platform to provide data and information to enable this cyclical transfer of data and knowledge to take place. So we've got here our mission, our vision, and our approach, which are covered in here. And very much our intention is to get towards a point where there is no energy performance gap between the design expectation from a building and its operational performance. And we look at that from those two perspectives, and one is how do we provide better data and information for the design process itself, and that could be new build, refurb, or leasing, as well as how do we improve the operational performance of existing buildings to better align through building performance evaluations process to their original design intent, and to better understand how we can deliver that. And there's a video which we've got. I've just put in the URL at the bottom if you want to find out some more information about CBX. In terms of what do we do as part of this program, we provide a series of breakfast sessions and evening sessions. And that's really from a knowledge perspective, and it's transferring of information. So we have speakers from the industry who will come in from across the design and the operational as well as the research perspective to provide some of that knowledge and information. A set of training workshops that goes into more detail as one-day sessions, and then also working with UCL Energy Institutes to provide some tailored and bespoke research and advice that gets provided to organisations from a data perspective, understanding the data, the accuracy of the data, and then how that information can be used. And really the bits that make us different is that evidence-based approach. So we utilise the Carbon Buzz platform, and within that platform we have approaching 1,000 buildings, and we have a program to input 1,000 buildings per annum into that platform. What that provides us with is not only the largest evidence base that we have in the UK, which is as an open platform, but the ability to be able to utilise that knowledge and the information to be able to benchmark very clearly where businesses are, where organisations and buildings are, but then also where some of those gaps and some of those issues do arise. So the first part of doing that is about data. And one of the main outcomes that came from the Technology Strategy Board's recent program on BPE, the BPE program, so it's the Building Performance Evaluation program, is the poor metering that takes place, both in terms of the accuracy of the data that's coming out from those meters, but also it's about the metering strategy that takes place. And traditionally and typically, we have a reactive process to metering strategy. So the first part is to put the meters in, and then the second part is to think about how we're going to utilise the data and the information that comes from it, rather than as the preferred approach should be to understand what kind of data and information we need, and then to install the right set of metering to be able to deliver the data that's required. And the data is absolutely paramount to be able to understand how we perform and to be able to make those the evidence base, to provide the evidence base, and to be able to make those informed decisions. And so the kinds of data and the kinds of information that we're able to produce and provide is just shown in these couple of slides. So we have, from a diagnostic perspective, this is a building that has been put within the platform, and we have the energy profile of the building, both as a comparison, which is a benchmark, and then from a design perspective and an operational perspective of a refurbishment of parts of a building. Within this, it tells us a huge amount of information about what the intention was of the building, as well as their starting point, and also where we are today, and therefore what is the additional elements that we can do to improve. And by using this kind of information and kind of data, it helps to improve not only the plant performance of the building, so this is the actual assets that we have, but also to link up from a behavioural perspective with the engagement of staff and also the supply chain on the services that get delivered. And as another example, we've got within here, we have a direct comparison of data that gets provided for a project, and then a series of similar buildings which you can compare yourself to. So the building that we have, which is at the top end, is provided as a straight gas and electricity supply, and then through the rest of the set of buildings within the platform, we're able to understand how that building compares against other peer groups. And on the right-hand side is a set of all the various filters and the information which we can accept information in. So that the key information is around the project details, the occupancy of the building, but we take data into a variety of sources, so we can upload data from energy performance certificates, display energy certificates, as well as more detailed studies such as TM22 and from energy bills as well. And so in terms of the key elements that comes out, I think what CBX is able to provide is that evidence-based approach, and we utilise the knowledge and information both from existing platforms, but also through UCL's Energy Institute knowledge and information to be able to provide an interpretation of what that knowledge and what that information means. The first event that we do have is on April the 3rd, which is around making energy audits work. And this is a breakfast session, 8:30 till 10 at UCL Energy Institute. And if anybody's got an interest in that, if they want to send me an email, we've got a small number of free tickets that are available, so I'm happy to provide those. And in terms of, just as a summary, in some of the things that we do need to do, there's a need to be able to communicate what energy performance means throughout the entire building life cycle. So from design stage through its construction, through the commissioning stages, and then into the operational stages. So what does energy actually mean for that building, and what is its intentions? And it's also particularly to look at the interfaces that is the critical part. So as we move through each of those stages, how do we transfer knowledge and information from one part onto the next part? So we remove and we break down the silos that we do have, and we transfer that knowledge through. And then it's also about making sure that we have realistic expectations, and at the initial stages of the project from a design perspective, and whether it's new build or refurb, that we have a true understanding of how the building can operate, but as part of being able to manifest that into a set of information and data, we can share that to the operational teams, who can then ensure that at the initial stages of a building, that you can recapture that, tune the building back up again, and enable it to deliver back to the original design intent that was put forward. And the key part is to be able to capture and share that feedback, and that's something that we're particularly poor on, is from an architectural perspective and the design perspective overall, is to go back to buildings 2 years in, 3 years in, and to ask the questions: what could have been done better? Where's the lessons to be learned? And what are you finding in terms of the operational performance of the building that you would have tweaked and that would have been changed afterwards? And it's only by capturing that and sharing that level of information that we're really going to be able to improve the performance of our building stock. So it's a quick run through and an introduction to the energy performance gap, and then in terms of how the CBX program fits and aligns with that. Thank you very much.
Great, thank you, Sunil. So we'll now hand over to Anna, who's going to talk through some of the things that they've been doing at Tesco. So over to you now, Anna.
Hi, I'm Anna Menezes. I hope you can all hear me okay. I'm going to speak today about the performance gap, focusing on non-domestic buildings and research I undertook into this topic. So, okay, perfect, that works. So I'll quickly start by introducing who I am. Then I'll run a brief introduction into the performance gap following through from Sunil's presentation. I'll then explain a little bit about my research, what I did, and what were some of the key findings. I'll then go into a very brief overview of the new CIDSI guide, TM54, which I co-authored and looked into predicting operational energy use at a design stage, and then I'll take us through some final conclusions. So, who am I and why am I here speaking to you today? Basically, I am an engineer with a background in architecture. I recently finished a 4-year-long engineering doctorate sponsored by ACOM and Loughborough University, focusing on the performance gap. Once I finished my PhD last summer, I embarked into a new, completely new world for me, which is retail energy management, which is where I am at the moment at Tesco's, and I also chair the Young Energy Performance Group. Today, my talk will focus only on my doctorate research, so really, unfortunately, not any questions to do with my role at Tesco. So, taking us into a very brief overview, this graph has information from Carbon Buzz, and it just gives a very brief outlook into the extent of the discrepancy in these three sectors: education, office, and retail. So as you can see, from a CO2 emission perspective, education buildings tend to emit 350% more carbon than anticipated at the design stage. With offices, that discrepancy is 170% and retail 175%. So that's quite significant, just to paint the picture. I am from a maybe slightly controversial position that, is there really a gap? Well, I've just shown you there is, but as Sunil mentioned before, we're not comparing like for like. So in a sense, I feel like what you can see in this graph here, that comes from Carbon Buzz as well. What we usually refer to as design prediction tends to only be your Part L calculation, and that only includes your regulated loads. Then if you do a full dynamic simulation, which doesn't happen as often as you'd imagine, then you might get to cover a lot of the unregulated loads as well. But very rarely do we consider extended use and other uses of the building beyond what was included in your original Part L model. So in a sense, I feel like there's more of a gap in perceptions rather than a gap in performance, because we need to be worried more about what we're actually doing instead of what we think we're doing, because the reality is we're not predicting operational energy use. We're complying with building regulations by providing a calculation that serves its purpose, which is just to compare a buildings from one building to another at the design stage in a normalized manner. But it's not, its intent was never to predict operational energy use. So it's not surprising that once we get operational energy use data, that both sets don't match. There's also a gap in communication, because in an ideal world, as Sunil mentioned, we would be feeding back information from existing buildings into new designs. As you can see in this diagram, so you design your building, you run your simulation, you construct the building, then you do some monitoring, and you get feedback into your next design, and also feedback into the same building to improve its performance. Unfortunately, that almost never happens, and after construction, the design team goes to their next project, and there's a bit of a lack of responsibility on who should be performing the monitoring and the feedback. Hopefully that's where Carbon Buzz and CBX can really come in and help facilitate this process. So what should we do to bridge this gap, be it in performance, perception, or communication? I think there are two very distinct elements on what we need to be doing. the reality is our predictions, so our design estimates, are too low. They're usually just your Part L calculation. They're not representative of real-life buildings. But also, our actual operational energy performance of buildings tend to be wasteful and too high. So we really need to be increasing our predictions and diminishing our operational energy use so that we could meet somewhere in the middle. So I'll briefly explain my research. I did engineering doctorate for 4 years looking at performance gap. And my focus was on the operational energy use of office buildings and variations in energy consumption by different tenants occupying the same building in different buildings as well. My focus was almost entirely on unregulated energy use in offices. So there was a lot of focus on small power, computers, general plug loads in office buildings. But also I ventured a bit into the realm of occupant behavior and the social side of things. The combination of my research was fed into CBTM 54, which is the new CIDSI guide I mentioned earlier, and I will cover again in a bit, which is all to do with how we should be predicting operational energy use at the design stage, going beyond just the Part L compliance. So just to give a quick insight into how big unregulated energy use is, this is an example of one of the buildings I monitored, and as you can see, the unregulated loads are almost half of the electricity consumption in the building, which was also highlighted by Sunil earlier, how large unregulated loads can really be. So if we're not accounting for these in your Part L calculation, then it's really, really no surprise that both design and actual consumption figures don't match. So looking at a specific building in central London with 4 different tenants, you can see in the blue bars that those are that's the small power consumption, so unregulated, or a part of the unregulated energy consumption in the building by the 4 different tenants, normalized by square meter. And to the left, the green bars are the best practice and typical benchmarks from Econ 19. As you can see, there's a significant variation between the different tenants, even though they all perform fairly similar activities, with the lowest consuming tenant, tenant A, using about half of what tenant B uses, the highest consuming tenant. And as you can see, they're all above best practice, but with the exception of tenant A, the rest is also above typical benchmarks. So that also highlights that not only is unregulated load a very big chunk, a very big portion of our energy used in buildings, but there's also a lot of variation. So a single number, even a single benchmark or a rule of thumb, is unlikely to be able to accurately represent the small power consumption by different tenants, even in the same building, as you can see here. So what I did as part of my research, this was the first study I did during my doctorate, was trying to predict the small power consumption in an office building by a single tenant, starting from the most basic approach, which is just your Part L compliance, and moving on to a more bespoke methodology. So this, I'm actually looking at lighting, small power, and catering consumption, which are the tenant side of the electricity consumption in the building. So this graph, as you can see on the left, you've got again your best practice and typical benchmarks from Econ 19, and all the way on the right in green, you've got the actual consumption for this one tenant, which, by the way, I didn't know at the beginning of the study. So with model number 1, that's just your typical compliance model, which includes only your lighting. No small power, no catering allowances. As you then include a rule of thumb, a behavioural rule of thumb for your small power, it brings us to quite a lot closer to reality, but still pretty far away, to be honest. And model 3 was an initial bespoke model accounting for the actual number of appliances and number of people in the building, but not adjusting for realistic operational hours, and not including miscellaneous plug loads other than the basics for computers and screens and printers. So as you include all the equipment you have in the building, you get, again, a little bit closer. And it's only in the final step when we change the hours of occupation to represent the realistic operational hours of the building that we actually get pretty close to reality, within 3%. As you can see, that was the final step for changing the occupancy hours. So I then went and tried to correlate a bit closer the profile of energy consumption during a given day with occupancy patterns, so when people are in and when people are out. And you can see in this graph that electricity and occupancy profile have a fairly similar correlation in their profiles, unlike the SBEM standard occupancy profile, which is what's used in your compliance calculations. The only two discrepancies, biggest discrepancies, well, obviously you've got your base load that never goes away, unlike occupants that actually go away at the end of the day. At lunchtime, you see quite a big decrease in occupancy numbers, but that doesn't quite show, it's not as prominent in the electricity consumption, as people don't really turn off their computers at the end of the day and the lighting's still on and so forth. And right at the end of the day, at around 8, 9 o'clock, there's a spike in electricity consumption that does not correlate with occupancy, but that's just to do with the cleaning rota of the building. So that's when the cleaners come in and all the lights come back on, and there's vacuum cleaners and dishwashers come back on. So you see a quite significant peak in energy, but not so much in occupancy. So fueled by this insight into occupancy behavior and what occupancy numbers do to occupancy behavior, I then went into, I developed a study in partnership with another researcher sponsored by ACOM, and we tried to investigate how much of occupant behavior, their actions, were impacting on variations in energy consumption. So that graph showing that the lowest tenant had about half of the energy consumption of the highest tenant, how much of that was to do with the occupant behavior? So we developed a study based on the theory of planned behavior, which is a psychological theory that determines that a person's intention to carry out a behavior is informed by three aspects, which is the behavioral attitude, so their desire to actually do something, their beliefs, a subjective norm, which is how they're influenced by their environment and by their colleagues, and perceived behavioral control, which is how much a person perceives to have control over undertaking that action. And all these three influence the person's intention to carry out a behavior. But the theory also suggests that perceived behavioral control is the only of these predictors that actually has a direct link to behavior, bypassing the intention. So the results from my study actually was quite interesting because it confirmed this direct link from perceived behavioral control to behavior. Because out of the three predictors, the only statistically significant correlation we found was for perceived behavioral control, demonstrating that this predictor accounts for 17% of the variation in energy consumption for lighting and small power in this building. So this suggests that the more control people perceive to have, not necessarily have, but perceive to have, the less energy consumption, the energy they'll consume. And what I find quite interesting is that this goes against our current design trends for more automated buildings. And it also highlights that occupant behavior is very complex, and it's not that straightforward that we'd be able to model behavior in our energy consumption predictions. But we need to account for it in some way if we're going to have realistic predictions. So that brings me to CIBSE TM54, which is the new guide published by CIBSE into evaluating operational use at the design stage. And this guide actually tries to account for a number of items that I've spoken to so far, including the behavior and the operational patterns of the building. So as you can see, this is a case study we used in the development of the document, and the case study building used less than a third of, the part L prediction for the case study building was only about a third of the actual energy consumption. And once we'd undertaken the TM54 estimate, that brought us a lot closer to the actual performance and within the predicted range of figures that were the output of the TM54 estimate. So just very briefly taking an overview of what the methodology entails is that you carry out a number of calculations outside a dynamic simulation model. These are the steady state ones that don't have any impact on weather and seasons over the year. And these will also, so there will be direct electrical consumptions, but also internal heat gains. And that is a really important thing because we tend to underestimate the internal heat gains from equipment, and also absolutely everything that goes within the building fabric will be emitting heat. So even your fan coil units, which you would maybe perceive as it being a form of cooling a lot of the year, but it's got moving parts, it's got fans, and it will be emitting heat. And it being within the fabric of the building, even if it is in the ceiling void, it will still increase the internal heat gains in your building, and it should be accounted for in your dynamic simulation model. So once you've calculated the internal heat gains, those are then used as an input in your dynamic simulation model, and very importantly, those are applied to realistic operational loads and operational profiles. So it will account for how the building is likely to be operated in real life. So we then suggest that a number of different scenarios are run and a sensitivity analysis are undertaken. You also should review your results against benchmarks for sense checking. And we also provide a number of suggestions on how you can present your results more clearly to the client. So one of the ways of presenting the results more clearly is by showing the ranges and the variation in the ranges expected from the different scenarios you're running, as you can see here, by individual end use. And we also emphasize the importance of presenting your assumptions in your results. And this is an approach that was originally implemented in TM22, which is a tree diagram approach where you can see how each input then contributes to your results. And we advocate that the same methodology be used when presenting the results to clients. And following through very much from what Sunil said, we also in TM54 advocate that energy performance be reviewed throughout the design process, but also after the building is completed. So this is not a one-time thing that you do at one point in design and never revisit. You should always be revisiting and adjusting your predictions as you go along and your design gets firmed up. So some very quick conclusions. We know there's a huge discrepancy between design stage energy calculations and operational energy use. One of the ways to reduce this gap is to do more realistic predictions of operational energy use at the design stage, and TM54 provides a really good methodology for doing that. And my own research also raised that occupancy hours and general operational patterns of the building are very important and need to be considered, going beyond just normalized standard assumptions used for Part L and building regulations compliance. Internal heat gains need to be realistically accounted for in dynamic simulation models. And in a sense, I feel like, unfortunately, but someone might have a different view, but a lot of the internal heat gains are determined and controlled by occupants, which makes it really difficult to predict because we're talking about a huge number of people as opposed to maybe just one facilities manager. So, yeah, thank you very much for listening, and that's me.
Great. Thank you very much, Anna. That was a great overview there. So we'll now go straight into the question and answer session. So we've had quite a few questions coming in, and maybe this is a good one to start off with, a sort of fairly general question, but Sunil, maybe you want to pick up on it. But someone's asking who should be leading this process. Is it the clients, the designers, the construction team, the facility managers? Who do you think is best placed to sort of kick things off around this topic? Hello, Sunil, can you hear me?
Sorry, hello? Yeah.
Hi, Sunil.
Sorry, I had it on mute, forgot to take it off. Yeah, it's not as such where a single person, a single group will lead on it. Everyone has their role to play, and everyone has certain sets of knowledge and information. So it's a group as a whole, how do you deliver and provide knowledge and information to be able to reduce this gap? And that comes from knowledge from the FM guys and the asset managers who can talk around some of the performance activities from a behavioural perspective and end user perspective, together with individuals from a design side who can talk around what that means for the design of a building. Ultimately, a client will pay for these activities and somebody will need to provide the funding for this. But we're looking at it from a life cycle perspective as opposed to a capital spend and an operational spend.
Great, thank you. Anna, there's a question here sort of relating to what you were talking about, is how do you predict what impact good occupant behaviour will have?
Okay, so that is really not a question that has a straightforward answer. I think I would have loved, as a result of my research, to be able to say, well, occupant behaviour can... So part of that theory plan behaviour study was that hopefully I'd be able to get one single percentage figure, let's say, that you could say occupant behaviour will account on average, about 20%, let's say, of your energy consumption, so you then apply a 20% error margin each way and you're sorted. Unfortunately, it's not that simple, and we could only find that percentage, which was 17%, for one of the elements of behavior, which is perceived behavioral control. Unfortunately, I don't think it's that simple. We need to, I think the best answer that I can give is that you need to account for at least the number of hours occupants are going to be in the building, and roughly how they are intending to use the equipment. So from a small power perspective, focusing on computers, for example, my research also found that if you are supplying desktop computers rather than laptop computers, the user is less likely to switch it off at the end of the day. So maybe that's something you need to account for in your predictions. But there is no one percentage that I think we can apply. We just need to apply judgment to individual items of equipment and general parts of the building that the occupant have control over, and run different scenarios. So a scenario where the occupant behavior is fantastic and there's no simultaneous heating and open windows and everyone switches their equipment off at the end of the day, and then run a scenario where people aren't that great, and just assume that your result will be somewhere in between those two extremes. That is the best I can really suggest.
From an understanding perspective, something that we've been involved in is almost surveying staff, so surveying the occupants to understand where they're coming from. So in that sense, you want to understand their attitudes to energy performance and what they do in their day-to-day activities. What that will provide you is that strong baseline of where you're starting from in terms of not only current activities and attitudes, but also their willingness to change and to vary their behaviours. So coupled that with the modelling aspects, it provides you with some very good information of where you are, but also where you can end up, and that will give you your potential improvements that can be delivered.
Great.
Absolutely.
Another question here, how do you ensure your meters are calibrated, and if you're talking about historic installations, how do you check that they are calibrated?
Yep. Anna, do you want to take that one?
Well, to be honest, it's not really my area of expertise.
Okay.
Well, you can put temporary monitoring in place, and you can compare the results. You can compare the results, the readings from your own meters, and what the electricity supplier is providing you. But in addition to that, I think it's just getting the experts in to often calibrate the meters. I don't know if Sunil has a more technical view into it.
Certainly for your fiscal meters should be accurate, and that's the responsibility of the energy company, your energy supplier, to do that. So in the first instance, it's to contact them for the fiscal meter, because we've got limitations on how much we can fiddle with them. For any of the secondary metering, we've got a greater control, and therefore it may be bringing in a specialist to recommission them and make sure they're accurate. But another way of doing this is just from a data perspective. And so in that sense, what we're looking at is reconciling the readings that we're getting with the total energy consumption values. So it's taken things like the AMRs, the automatic meter readings that we get, and reconciling them with the total energy consumption. So it's a paper check from two different sources to make sure that the numbers do tally up.
Great, thanks, Neil. Anna, there's a question here for you. Are you managing to find a way to take the realistic expectations of your building and feed these back into the start of the process and create a building that is optimized for operational energy? For example, the refrigeration cabinets which are used in supermarkets.
Okay. To be honest, I've only been at Tesco for 2 months. I can't really comment. I've not really been allowed to comment on my work here, as I'm fairly new. What I can say is that at ACOM, where I was previously based, we were very much trying to use real data for real buildings to feed it back into the design stages. I developed a model for predicting operational energy use of small power computers and equipment based on a lot of detailed monitoring data, and that tool is now available to the designers within the company to use in order to predict the operational energy use and internal heat gains of small power equipment in offices. I think that is personally, I think that's the way forward. I'd like to believe that here at Tesco we will be doing that as well, and to a certain extent I feel like it's already being done, but it's not something I've quite been involved yet. And there are a number of different teams. I don't deal with predictions here. I only deal with measuring operational performance of stores. So no, I think it's absolutely the way forward, and it's the way to go, the only way to go. And hopefully it's where CBX can help a lot.
Yeah, I mean, certainly in some work that we've been involved in previously, we've worked with a major petrochemical company, and they had a number of buildings around the globe, and their total asset spend was in the region of 650 million per annum. And the program that we developed was the diagram which I showed, which was to collect the operational performance data from a behavioural perspective as well as from an environmental perspective and a supply chain perspective. And so we understood what that performance was on a building-by-building basis, and we collected that data at a quarterly level and had discussions with the individual asset managers and property managers to understand the information. All of that knowledge in terms of the behaviour of the individuals in a building as well as the actual environmental impacts was then fed into the design process of any refurbishment that took place or any new build activity that was then performed. So we understood at the very beginning what the kind of building that we were looking for from a behavioural perspective and also from an environmental perspective. And that was captured in 2 books. We had a green book and a blue book, the green book from the environmental side and the blue book from the behavioural perspectives. And that was communicated to all parts of the supply chain. So the not only internal within the organisation, but also to the constructors who were involved in the project, any agents that were involved on our behalf. as well as the end user receive those books. So we had a single form of communication and a very robust evidence base which we're able to use to be able to drive those changes. What that led to was double-digit savings in terms of the performance of those buildings, both in terms of savings from a design and operational perspective, as well as just simply from sharing knowledge and information that existed from good practice across all of the buildings. And so it's that kind of methodology that we're looking at providing from a CBX perspective that takes that robust knowledge base and then talking about how we utilise that not only for existing buildings and improving the operational performance, but also for the design and the refurb process.
Great, thanks, Neil. So conscious of the times, but I think we've got just enough for one more question, and a good one to end on, I think, is are there certain pitfalls you should be conscious of or caveats when comparing benchmarks for your sector? So ensuring that you're comparing sort of apples for apples. Are there certain things that can crop up and sort of throw those figures out? Yeah.
I mean, certainly... sorry, go on, Anna.
No, it's okay.
Certainly, the three things to look at when we're doing our energy information that's provided through CBX. And the first one is the occupancy, and understanding not only the number of people but the hours that the building is operational. And as Anna's already said, that has a huge variation in terms of those benchmark figures, and also from a comparison perspective to be able to compare yourself to somebody else. You want to understand, are they running their building for 10 hours a day or for 15 hours a day? The second part is an understanding of some of the fabric elements of the building. So just some of the information around the age of the building and the kind of external fabric that it does have. And the third part is the energy consumption itself, but a breakdown of some of the key elements of energy that's being consumed. So again, for that, we want to understand, is there a restaurant facility that's within the building? Is there a computer suite within the building? So the items that consume significantly higher and a disproportionate amount of energy, if we can ring-fence them out, then we end up having a floor that consumes energy on an hourly basis that should be comparable from an office building to an office building, or a small retail to a small retail, or an educational facility to an educational facility. So all of that just comes down to good data that's being provided.
Great. Well, that's all we've got time for. So I'd just like to thank Neil and Anna for their time today and for getting through so many questions, and also for everyone who's joined us for this webinar. Just to remind you all, a recording of the webinar and the presentation slides will be archived on the 2 Degrees platform. So I hope you found today interesting and useful, and you'll be able to join us for future webinars in the coming months. So thank you.